Hello, I'm Nate Fosse. Today we're going to explore in this R tutorial probability, that is logical probability, using three particular functions. In the next page I'll show you what these are. The first function is the deal function, which in this case we're going to look at dealing cards or shuffling, dealing out a number of cards from a deck. The standard 52 deck of cards, if you've ever played any particular card game like bridge or a game of chance such as blackjack or poker, then the deal function using the 52 card data set, which is built in within R, should be quite familiar. This second one, the second function is we're going to show how to create a data set flipping coins, doing flipping a fair coin. So next time you're in doubt about the relative likelihood that your friend had flipped a coin fairly, you can direct that person to the R programming environment and use the R flip function. And the third function we're going to look at to explore probability, logical probability, is this do function, which is built within the Mosaic package. And it's short for doing things repeatedly. And these are three useful functions, not just to simply play with games of chance, but actually to understand and explore probability and to create data sets that we can then actually generate and examine. And I want to emphasize that these are relatively important when we think about broadly when we use statistics in general, because quite often when we say analyze or examine the attributes or the limitations of a new statistical technique, we're actually often creating a sample data set, an artificial data set, wherein we control the parameters or the features of that data set. So that way we can examine, well, what happens if we alter something with the data set? What does that mean regarding our statistical technique? So I want to underscore the main point here is that not only are random functions part of the R environment, but there are also ways to create simulated data that we can then use to examine statistical techniques. And that's of course farther down the line, but for right now I want to just use this as a sort of an introductory invitation to explore some interesting properties of probability. At this point you should be able to download from the problem set webpage both the R script, which is this problem set 3 rcode.r file, and then the GSS data set, or the R data set. In this case we're looking at health data because you're wearing the hat of a social epidemiologist. And you should, in terms of what we often refer to as workflow, you should put your script and your data within the same folder. And we call that workflow in computational statistics because we want to emphasize that when we run an analysis, a statistical analysis, we like to keep our code and our data and our projects in particular within the same folder. So I recommend, as I have explained before, to keep your script and your data within the same location. Of course, if you have more complex projects, you will have maybe subdirectories, subfolders there. These are relatively more simple, just simply the syntax and the data set. And I'm assuming you have this already built into your environment. And of course, if we run the script here, we're going to actually load the data set and the library and the packages, and we've already done that. I'm not going to review any of these questions or comments about using the tally function, because I think these are relatively intuitive, and I've covered them before when examining two categorical variables. So I recommend you revisit my R tutorial on tabulation of two or more categorical variables. What I want to deal with instead, pun intended, are these three random functions. And I think I know they're quite interesting because probability itself is quite difficult to grasp, I think, for many people, and myself included, in part because so many features of probability are counterintuitive. I want to show you first, and I'll explain this when we use the deal function. So deal, what is this? What's the deal about deal? The deal function here simply takes a data set. In this case, we're taking our standard 52 cards in your standard deck of cards, which is about, I was looking this up before preparing for this tutorial. It's about 500 years old, the standard deck of cards. And this is a built-in data set. And what we're doing is pretend like you're shuffling your cards and you're dealing out these cards, and you're going to hand to someone. Maybe you're a magician, maybe you work in a casino, maybe you're just playing with friends. You're going to hand somebody one card out of those 52 cards. And that's what this second argument is after this little comma here. So this takes the built-in data set of the 52 cards that we have within R, and it deals rather one of those cards. And let's just see, in terms of probability, which card we get. So we'll be able to see this. Well, here we have a card called 7S. Well, what is 7S? Well, that's the 7 of spades. Now, of course, we can deal out 3 cards. Typically, we're not only dealing 1, but here we have 3 cards. Notice, of course, when we talk about probability, we're not only talking about just one random draw, but sometimes we're also talking about a sequence of random draws. So in this case, that are, by the way, in this case, related, because if you draw one card, then you're also drawing another card minus that first one. So if that makes any sense. In other words, if you're dealing out the Queen of Hearts, then you have a data set of 50. Then you only have 51 cards left, and then you have to deal out the 5 of diamonds, another card, and then another card. So the point here is that we can use probability functions to deal out cards, and that probability can be understood in terms of sequences. And we often refer to this as a factorial in mathematics. This idea that sometimes probabilities are not only, say, a flip of a coin, which is what we'll go to next, but it's also the probability of getting these particular cards in this particular order. And I'm going to do something here that is, I think, quite interesting. And it was actually revealed to me, rather popularized on a British television show by the British actor Stephen Fry, who had announced that he would do something that has never been done in the history of the universe or in humanity. And how can this be? Well, what he did actually is he went on a show, on his show. It's called QI, and I'll link this on the course website. I can't provide it here for probably for copyright reasons. But what he did is he shuffled a deck of your standard 52 cards, and he provided, and he said that this deck of cards actually, the odds of getting this particular sequence, in his case, it's infinitesimally small, that one could actually shuffle a deck of cards and deal out all 52 cards in that particular order. And I'm going to show you, I'll explain this a little bit better, I think, when I print out. I'm going to shuffle. So in other words, I'm going to deal the whole deck, and you're going to see within the console all cards. So here I have dealt out every single card in your standard 52 deck. And what we have here is this sequence of cards. Now, if you know something about statistics, then you might be aware of this idea of factorial. And the point here, this is a little bit, you know, maybe a stray from the main point in the course, but I think it's really fascinating and exciting to think about. What are the odds of me actually shuffling this? Well, Stephen Fry pointed out rightly that what I have just shown to you probably has never ever happened in the history of humanity, because the odds are so slight that any person would have actually shuffled a deck of cards that is in this particular order: a queen of hearts, 2 of clubs, 6 of hearts. I know this sounds strange, but the way to think about this is in terms of probability. And the probability of this sequence, this particular sequence, is what is known as 52 factorial, which is 52 times 51 times 50, all the way down to the lowest integer. And I'm just going to use this factorial function. You don't need to know this. I'm just going to show you. This is the probability of shuffling this deck in this particular order. It is 8 times, about 8 times 10. So it's about an 8 with 67 zeros. I'm going to copy and paste the actual full number here, just so you get an idea here. This is what the number actually looks like. It is about this long. The odds of me shuffling this deck, and when you deal this deck, the odds are about yay big. And you'll see actually, if you look at the scientific notation, all that I printed down below are these first few digits, rounded up, and then basically we've said, okay, we're just going to add 67 zeros here. But this is the full number. This is the odds of dealing 52 cards in this order. In fact, we'll do it again, and we'll see that we actually got a different order, and a different order, a different order, different order, different order. Now you could probably do this all day. I am curious to see if you'll actually deal these cards in this order. Well, what are the odds of this? Actually, if you looked at the sort of the workspace, there actually are, according to what is known as the Shannon number, which deals with the probability of the number of moves on a chessboard. That seems to be higher than this. But I also, along the way, just wanted to see if this number is actually larger than the number of atoms in the universe. And in fact, it actually isn't. There are actually more atoms in the known universe, probably, according to most recent estimates, than there are this number. But really, the odds that when you do this at home, are going to get the same shuffle as I have here in terms of this particular shuffle or this particular shuffle, or the odds that I'm going to repeat this, is infinitesimal. So I'm actually going to say just kind of quote Stephen Fry from his video. He says, to kind of give an intuitive idea, he says that it would, to give you an idea of how many, the number of possible, so this is the number of possible permutations. We can sort of think of this as a permutation by probability. So to do this, to replicate this, how long would it take? We could ask that question. And according to Stephen Fry, it would be to go through every possible permutation just here in our deck of cards. If every star in our galaxy had 1 trillion planets, each with 1 trillion people living on them, and each of these people had 1 trillion packs of cards, and somehow they managed to make unique shuffles 1,000 times per second, and they've been doing this since the Big Bang, they'd only now just be starting to repeat these shuffles. So as far as I'm concerned, and as far as anyone else is concerned, you probably, if you're wondering if you've ever done, you wanted to know if you've ever done something that no one else has ever done before. We all want to do that, right? When we're doing our work, when we're being creative, I can give you a very easy way to do something that nobody else has ever done before, and this is quite fun, which is to use the deal function in our deck of cards, and create this permutation. So that's just a simple function to explore some wild aspects of probability. But I also want to show you a more simple one, which is just how to flip coins. Here we are. Here we see flipping coins one time. You can do it once. You'll get a head or a tails. And then here we have a probability that's exactly 0.5. So it's a fair flip. Now we can also do this in terms of repeat runs. The point here is when we talk about these coin flips, these, unlike the deck of cards, which is depends on the order of the cards, these are actually independent probability trials. In other words, in this, now of course this may not happen when your friend is flipping a coin. You know, they may try to flip it differently, but the point I'm trying to make here is that we could flip a coin here and we may get a tails. But when we flip the coin again using this function, it's an independent trial. So here we have 5 independent trials. So sometimes you may actually see a pattern in the data when you, say, do independent trials, which means essentially when I talk about independent trials, I'm saying that each coin flip is independent of another. In other words, knowing whether or not you got a heads or a tail the first time you flipped the coin tells you nothing about whether or not you got a heads or a tail the second time you flip the coin. This is in contrast to dealing cards, because when we deal 1 card, or when we deal 3 cards, or when we deal all 52 cards, the dealing of these cards, the probability of, say, dealing the second card is conditional on which card you removed from the deck, right? If I'm dealing a deck of cards and I deal out, say, the 2 of clubs, well, that removes the probability of me dealing a second time the 2 of clubs, because that's already out of the deck. But when you're flipping coins, these are independent probabilities. And the point here is that there's something that humans fall heir to when they flip coins, or when they even deal with independent probabilities. And I want to emphasize this idea of independent as opposed to conditional or dependent logical probabilities. And these are logical probabilities because they're not based on our subjective opinion. When we deal with independent probabilities, we can see that sometimes we can be fooled by randomness. To quote a rather popular book, let's say I'm flipping coins, and I'm thinking this coin is rigged, because if we look at these last 1, 2, 3, 4, 5, 6 trials, and I refer to these as trials because it's sometimes the language of what is called a binomial distribution, we'll actually see that this coin looks kind of rigged based on these 10 flips right here, because I only got 2 tails and the rest were heads. Well, it looks like the proportion, and we see that proportion right here, it seems like, well, gosh, 80% of the time I'm getting heads. So the point here is that we can be fooled by randomness when the sample size is quite small. But in the long run, if we flip the coins a gazillion times, it'll actually be closer and closer to 0.5. But this is important because it actually reveals some of the difficulties in interpreting probabilities. In the short run, the fallacy of misinterpreting or mistaking independent trials, random probability trials, such as the random coin flip, as something that is sequential, is known as the Gamblers Fallacy. And you could imagine how this could be the case, because someone, say, playing at a slot machine, assuming the slot machine is truly random, may actually believe that there's some meaning to the order, to the sequence of independent trials. So the main point here is that, especially when we look at a small number of independent trials, we have to remember and ask ourselves that whether or not the probability of an event that is happening. Say, especially when we talk about games of chance, are these events conditional probabilities, or are they independent of each other? And of course, in this function, the rFlip function, it's a random flip where each trial is independent. So the fact that we just happen to have 80% of our 10 coin flips to be heads, it means nothing. And if we were smart and careful about our probabilistic thinking, we would understand that this sequence really means nothing. And it's, of course, there's a reason there's a name to this kind of probabilistic fallacy called the Gamblers Fallacy. It's because it's quite common to think that unrelated events are somehow related. So to give you an example, let's look at what happens when you do 50. Let's do 50 coin flips, and I'm going to actually just use the this do function, which is actually quite broad. It simply means do repeatedly. So you just have the word do, and in parentheses you have the number of times you want to do something, and then you have this little asterisk, which is simply a kind of a multiplication operator, which says we're going to do this 5. So in this case, we're going to do whatever it is we want to do after the asterisk 5 times. So in fact, we can actually do even text. So I'm going to print in the console 5 times hello. There we go. So now we're going to look at coin flips, creating a data set of coin flips. And after exploring the do function, we're basically going to make a data set of 50 people, hypothetically, and see what happens when each person flips a coin 10 times. In the language of syntax, or logical syntax, what we're saying is we're defining as a new data set. Right? Here's the assignment operator, and we're going to call this new data set coin flips. We're going to do 50 times a sequence of 10 independent coin flips. So this is, in essence, like 50 people. Let's say we take 50 people and order them to say, and we say, we're going to have each of you flip your coins, and we're going to count for each of you the number of heads that you had gotten, or the number of tails that you have gotten. And I'm going to show you why this matters in the sense that when we think about independent trials, a short run sequence of, say, 10 coin flips may appear to be somewhat biased, in the sense that a coin flip may appear to have a sequence, and the probability of heads may be other than 50%. And the insight we have that I want to point out here is that when you have independent trials, as the number of those independent probability trials increase, in other words, as the number of independent coin flips we have, the more people we have doing independent coin flips, the closer we get to the long run probability of 50%. This is akin to the idea that in the house always wins, as the Las Vegas casino expression goes. The idea simply being that perhaps if you are flipping a coin or doing any kind of game of chance, you may win in the short run, but in the long run, the odds will be against you, or the odds will be whatever are defined by the rules of the game. In this case, in this simple example, the coin flip in the long run is 50%, as long as it's fair. In the short run, you might be able to be lucky enough to have all heads 10 times in a row. But in the long run, the more coin flips you do, the more people doing those coin flips, you'll see that this converges to 50%. 50%, or a proportion of 50. And I'll show this to be the case here with this data set that I'm going to create using the do function, or do repeatedly function. So we're going to create this data set called coin flips, and here we are. We just created it. Let me remove an earlier version of that, and let's use the view function just so we have an idea of what we just did here. Let's view our data set. Well, here we have in our first column in our data frame, or data set, we have the rows, and this counts to 50. And you can determine this by using the number of row function. We can just confirm that we have 50 rows. Indeed, we do. And of course, another function to explore data is the number of columns and call. This will also give us an idea of the data set. If we want both dimensions of the data set, we can do columns and rows. And this will give us first the rows and then the columns. That's just another way of exploring the data. Typically, in the RStudio environment, this is the number of rows and columns are pretty transparent. But what I want to show you in this data set is clearly you can see that we have 50 rows, 50 simulated repetitions. In this case, hypothetically, imagine we have 50 people. Each person flips a coin 10 times, and we can see that each of them has separate probabilities. So, in fact, if we look at the probability if we use the filter function, we should be able to look at these people. It looks like the highest proportion is 80%. We can see that we have a few people here who may think that they're getting far more heads than they would have expected, right? So in these extreme cases, you may encounter the Gamblers Fallacy, and that's what I had shown earlier with 10 coin flips. But what I want to show you is that we should be very careful when we talk about these probabilities, when we're talking about independent probabilities. So let's use the tally function that we've used before. And what this shows is a count of the number of heads in our sample. It's the probability of getting of heads by its frequency. So here we have, I'm going to show you a figure. We're going to use the dot plot function because we have a rather small data set. And we can see that our probability pretty much matches 50%. We would expect in 10 coin flips that are independent, as we know, because we're using a random function. We would have 50% of the time we'll have heads, 50% we'll have tails. But what I want to show you is that there's because we're dealing with probability, there's some random variation going on here. But on average, in the long run, the probability will converge around 50%, and that's where the distribution somewhat lies. Interestingly enough, we seem to have more 6s than 5s, but 6 is closer to 5 than 7. And of course, we have fewer 7 counts of heads, 7 out of 10 coin flips. And we, of course, fewest in these extreme cases. So let's see what happens when we, why don't we just do this again, and we're going to do 500. And we're going to recreate this, and we're going to tally this. And look what the, in fact, instead of doing the tally, we'll just do the mean of the proportion, because we actually have the proportion of heads here as our third variable. So I'm just going to use our mean function that we used before, and we're going to calculate the mean, the mean proportion of getting heads in a much larger data set. So we're taking 500 people and having them each flip 10 coins. And what we'll see is that this is going to be very close. We have an error here. Let's see if I can fix this. Oh, I know why. It's a very simple error. It's because we need to tell RStudio that we're defining coin flips as our data frame. So here we created the data set with 500 people now. We recruited 500 people. And okay, well, that's pretty close to a probability of 0.5. And in fact, probably closer than it was when we had fewer people, I'm sure. But now let's increase this to 5,000 for help. We'll do 50,000. And we're going to do the mean of the probability of getting heads in 50,000 people. So we should have done that. Let me confirm that we actually created that data frame. We actually didn't, so let me recreate that. It's taking a little while because it's taking, this is a larger data set, and this is one thing you have to deal with simulated data. But what I want to point out here is this is actually extremely useful when we talk about statistics, because the fact that we can simulate data rather than collect data and actually have people in the real world randomly select these values is extremely beneficial, because it's cost efficient, it's affordable, and it's a way for us to explore aspects of statistical models. Now it's still thinking, so we're gonna pause a little bit and wait until this data set is constructed, because this is 50,000, I believe, right? Unless I put an extra zero there. Yep, 50,000. It'll take a little bit longer, so we're gonna wait. Okay, it took about 5 minutes to create this new data set, which is if we use the dimension function, the DIM function, we'll confirm that this is a large data set. We have 50,000 people. This is a small town. And let's use our head function to see what this larger data set looks like. Okay, we could pretty much confirm that it's what we expected it to be. And if we have 50,000 people, each doing 10 coin flips, what should it look like? Well, we should have a number that's closer to 0.50 than we did when we had a fewer number of people. Let's see if we get closer to the probability of 0.5. So let's actually, I'm going to copy and paste this syntax here. And the reason I'm using the console, I want to emphasize, is that this is a little bit off of the problem set script, but I think it's useful, it's fun, and I think it's important to take a look at. So let's look at the mean proportion of coin flips when we have 50,000 people each flipping 10 coins. Well, it's close, but only a little bit closer than a fewer number of people. In fact, not much closer, to be honest. So you can see, actually, I already successfully completed this. So the point is, really, the idea of a gambler's fallacy, well, I mean, there are a couple points here. One is that once you reach a certain threshold, you have a number of a sample size that's large enough, you reach the probability of that function pretty accurately. But if you're only one person doing 10 coin flips, you may be somewhat skewed. Or if you're doing if we do this again, one person doing one sequence of coin flips, it seems quite inaccurate. If we do this 5 times, and then we average those, you see that it's a little bit less accurate. Right, because here we see, well, what does it mean here? I'm not going to create a data frame here, but you can see that this actually comes a little bit closer to the long run frequency of 0.5. Anyway, long story short is that you can deal with random functions, logical functions within the R environment. They are useful tools to explore probability and to understand the nature of probability. In addition, they reveal attributes of probability that are different in different contexts. When we talk about coin flips, they're independent functions independent trials, and they're unrelated, and that can lead to fallacious thinking, or which is often referred to as the Gamblers Fallacy, if we don't consider the fact that quite often when we deal with games of chance, probabilities are independent. On the other hand, probabilities are also conditional, and that means that we're incorporating not only the fact that we have a random draw from a sample, for instance, but that probabilities are conditional on each other, and that the ordering of a deck of cards when you're dealing cards matters. And so these are two different ways of thinking about probability: conditional probability with a deck of cards, and probability of independent trials when we think about coin flips. And the other, I think the sort of the overall story I want to emphasize is that probability is difficult to grasp. It's counterintuitive. That's okay. This is probably one of the more difficult sequences when we talk about the theory of statistics. But I think it's actually one of the most fascinating and interesting features of probability. The idea that you can actually do something that has never been done before simply by using randomly shuffling a deck of cards, as we've done in our data sets, I think is fascinating and very telling about the nature of probability. Okay, thank you very much.